Good morning, everyone. My name is Shariq Haseen, and I'm a graduate student at the University of Texas at Arlington, and I work with Dr. Kroll. The topic of my presentation today is about the development of a reactive force field, REACs, for simulation of silicon-based polymer-derived ceramics. So a quick background about these polymer-derived ceramics, or PDCs. PDCs are advanced ceramics with a list of notable properties, including high temperature stability, resistance to oxidative degradation, high creep resistance, and much more. For pyrolysis temperatures between 800 and 1300 degrees Celsius, SiBCNO PDCs are best described as an amorphous glass-like SiBCNO phase with an embedded free carbon phase. The amorphous glass-like phase is a mixture of silica, silicon carbide, silicon nitride, and boron oxide, depending on which elements are present. PDCs have many applications, including commercial products such as the Starblade brake disc and silicon oxycarbide glow plugs used in diesel engines. As you may have heard earlier, the LEAP engine produced by CFM International utilizes a ceramic turbine shroud containing PDCs. In order to investigate structural properties of PDCs, along with the polymer to ceramic conversion process of polysiloxanes, we use the reactive force field REACs, a bond order dependent potential developed by Audrey von Duin while he was at Caltech. REACs can be parameterized to have density functional theory, or DFT-like accuracy, while being able to simulate system sizes 1,000 times larger than DFT. 100 million atom simulations can be routine in REACs. Additionally, by allowing bond breakage, REACs can better describe chemical reactions than other empirical potentials. Different parameterizations of REACs have been done to simulate silicon oxycarbide PDCs, including successful work from our own group about the pyrolysis of polysiloxanes into silicon oxycarbide ceramics, as well as separate work by Vashist studying mechanical size effects of silicon oxycarbide ceramics. In this talk, I'll focus on REACs parameters for silicon and nitrogen interactions for later use in investigating the polymer to ceramic conversion of polysiloxanes. While there are existing REACs parameters for silicon and nitrogen, these parameterizations were used to investigate the oxidation of silica and silicon nitride surfaces, and they have their limitations. So we have to develop our own parameter set. Our method for fitting REACs parameters is straightforward. We utilize a huge library of existing and hypothetical crystalline models, along with hundreds of amorphous models. We train parameters on our library of models calculated within DFT as implemented by VASP. For DFT calculations, we use the projector augmented wave method to describe atomic cores and the generalized gradient approximation as parameterized by Perdue, Burke, and Ernzeroff to describe the electron exchange and correlation energies. Our aim is to establish a correspondence between REACs and DFT. Then we generate melt quench models in REACs through molecular dynamics simulations in LAMPS, and we map these models to DFT. This self-learning process is used to further improve the REACs parameters. We also include dynamical processes and reactions within the training. Since we seek to investigate the polymer to ceramic conversion process, we check how well our parameters reproduce the properties of solid-state silicon nitride. We calculate energy volume curves for crystalline forms of silicon nitride with REACs, as you see on the left, and compare them to DFT results, as you see on the right. Data is fit through a spline fit. We show energy volume curves for alpha silicon nitride, gamma silicon nitride, and a hypothetical willemite silicon nitride. Alpha silicon nitride is an ambient pressure phase of silicon nitride, while gamma silicon nitride is a high density, high pressure phase that was only first synthesized 20 years ago. Meanwhile, willemite silicon nitride is a high density, hypothetical polymorph of silicon nitride. These energy volume curves are all relative to the lowest energy structure of alpha silicon nitride. Generally, Our Reacts data performs well near the minima of the curves, but is not so good at very low volumes or very high volumes either. Otherwise, Reacts gets the trends correctly since scaling is only isotropic. Reacts is reasonably good for alpha silicon nitride and to a lesser extent willemite silicon nitride, which you see in the structures below, where the blue and cyan atoms are silicon and the green atoms are nitrogen. Both alpha silicon nitride and willemite silicon nitride contain only tetrahedral silicon, but willemite silicon nitride is substantially denser than alpha silicon nitride. Gamma silicon nitride contains both tetrahedral and octahedral silicon, and reproducing the gamma silicon nitride energy volume curve in Reacts is a bit difficult. Meanwhile, we also compare Reacts energy differences relative to alpha silicon nitride to those calculated by DFT. The lowest energy polymorph of silicon nitride has actually been computed to be beta silicon nitride, and our parameterization of Reacts does a good job in predicting the beta silicon nitride and gamma silicon nitride energy differences. The only real issue we encounter is having the energy difference associated with willemite silicon nitride as being a bit too low in Reacts, and this may be the result of some weaker homoatomic repulsions. Though we emphasize good reproduction of the thermodynamics, we also do some assessment of elastic properties. Here, we calculate the bulk modulus for alpha silicon nitride. The bulk modulus is calculated using the second order Birch-Murdigan equation of state fit to the energy volume curve. Since the Reacts energy volume curve for alpha silicon nitride is a close fit to the DFT energy volume curve near the minimum, the Reacts bulk modulus is only a bit lower than the DFT bulk modulus. Well, the DFT value agrees well with the experiment already, so there's room for improvement of the Reacts value. In order to assess whether changes in Reacts energies agree with changes in DFT energies, we calculate DFT and Reacts energies for hundreds of hypothetical crystalline silicon nitride structures. The plot of the energies relative to the energy of alpha silicon nitride is shown here. There's a moderately strong correlation between Reacts and DFT energy differences. The slope of the line of best fit for this data is around 0.5, meaning that Reacts energy differences are about half as much as corresponding DFT energy differences. Ideally, there would be a one-to-one correspondence between Reacts and DFT energy differences, but we're still getting there. And you can see some of the structures on the right that we use for this energy correspondence plot. Because we're interested in the temperature range in which PDCs are amorphous, we emphasize generating amorphous models in Reacts that match those produced in DFT, or get as close as possible anyways. We generate amorphous models in this case by heating up a supercell of alpha silicon nitride to 2000 Kelvin and then cooling it back down. You can see one of the structures here. Structures appear to become amorphous in a range of 1000 Kelvin to 1500 Kelvin during the heating process, and they change little for the remainder of simulations. The final structures exhibit mostly 4-coordinated silicon and 3-coordinated nitrogen. As mentioned earlier, since we are studying the polymer to ceramic conversion of polysiloxanes in Reacts, our parameter set must also describe molecular structures. And we calculate the energy of molecules containing silicon, nitrogen, and hydrogen, and these are just fragments that can be found in polymers. So we calculate the energy as a function of silicon-nitrogen distance and compare it to energies calculated with quantum chemical calculations, applying second-order Moeller-Plesset perturbation theory, or MP2. Here, energies are relative to the lowest energy structure in each diagram. Reacts does a good enough job with tetraaminosilicate, which has 4 silicon-nitrogen bonds, and you can see that in the diagram on the left. But as the Reacts curves, or as we go from left to right, the react curves do progressively worse as the number of silicon-nitrogen bonds in the molecules decrease. It's not shown here, but react's calculations of a trisiloamine, which has no nitrogen-hydrogen bonds, fit nicely to MP2 data, suggesting the problem here are the nitrogen-hydrogen interactions. And the impact of hydrogen on nitrogen may increase the bond order of silicon-nitrogen so that the silicon-nitrogen bond is shorter. So silicon or nitrogen-hydrogen interactions need some adjustment, likely. We use reacts to simulate perhydropolysiloxane, or PHPs, a polymer with a silicon-nitrogen backbone. With constant model simulations, we find that our model of PHPs remains intact at 300 Kelvin. Any visible fragments are only a consequence of how the model is displayed. There doesn't seem to be any noticeable problems. No unusual angles involving silicon and nitrogen, or any premature formation of gaseous species that may be found at elevated temperatures like hydrogen or ammonia. Now, further simulations of PHPs are done at elevated temperatures. We heat PHPs up to 3000 Kelvin at 10 Kelvin per picosecond. By 1400 to 1500 Kelvin, the silicon nitrogen backbone has deteriorated and the first signs of gaseous species forming can be noticed. You can see the ammonia that I've marked with a red arrow. Additionally, we also perform molecular dynamic simulations for the polysiloxane Saraset at elevated temperatures. The model on the left is the Saraset polymer. Simulations in reacts at 300 Kelvin cause everything to clump together, but no reactions occur by this point. After heating Saraset to 3000 Kelvin and then cooling to 300 Kelvin, the model changes quite a bit. Methane, ammonia, and hydrogen have evolved. And you can see some chunks, some silicon carbide-rich chunks in the model. Well, with our current parameter set, we don't quite see the formation of any ternary silicon carbon nitrogen chunks that we may be looking for. Although we don't do any removal of gaseous species yet, so that will need to be implemented in subsequent simulations. In summary, we parameterized a new set of reacts parameters. We evaluated silicon nitrogen parameters by calculating energy volume curves for silicon nitride and found that reacts generally agrees with DFT, though encounters some issues with low and high volume structures. Using the energy volume curves, we calculated that the reacts bulk modulus for alpha silicon nitride was close to the DFT value. Additionally, we found that reacts energy differences do correspond to DFT energy differences, though for these parameters, reacts energy differences are only about half the value of DFT energy differences. Anyway, molecular dynamic simulations were performed on alpha silicon nitride in order to generate amorphous models. And we care a lot about how these amorphous models look. So the models that we produce within reacts are not too far from models produced within DFT. In regards to molecules, reacts parameters slightly underestimate the optimum silicon nitrogen distance in small molecules versus in bulk silicon nitride. However, parameters were good enough to keep PHPs intact during simulations at 300 Kelvin without any premature reactions. Simulations of PHPs and Saraset at elevated temperatures did not encounter any real problems, but they still need to match DFT better. In general, we find that even though the reacts parameters aren't quite there yet, they're getting close. Of course, we also want to avoid any dangers of overfitting. Okay, so that's it. I'd like to thank the Kroll Research Group for their support. Thanks to the NSF PIRE PDC program for funding, of course. And thanks to the Texas Advanced Computing Center and UTA High Performance Computing Center for computing resources. Thank you for listening.